Hi guys, so in our lesson today, we are going to revise Chemistry Paper 1 2023. So before we start, I want to say this video is not only meant to introduce the KCSE Chemistry Paper 1 2023, but also act as a revision tool. You know, something that will help you recall the information or the content that you've already been taught, and also gently introduce you to topics that you've not yet encountered. So happy revision and let's start. So our first question goes as such: the atomic number of nitrogen and fluorine are 7 and 9 respectively. Draw electron dots and cross diagrams to illustrate bonding in the molecules of nitrogen and fluorine. Now let's pause there. Nitrogen and fluorine form diatomic molecules. This simply means that you're going to have a molecule of nitrogen, for example, having two nitrogen atoms covalently bonded with one another. So in this case, we are talking about an illustration of covalent bonding in nitrogen and fluorine molecules. And remember, when it comes to covalent bonding, we are talking about sharing of electrons. Now let's start with nitrogen. As told before, nitrogen has the atomic number of 7. This refers to the number of protons present within the nitrogen atom. And as is the case with any atom, the number of protons is always equal to the number of electrons. So we are going to have 7 electrons too. Now if we were to place these electrons in their energy levels, we will get an electron configuration of 2, 5. Now, as you can tell, this is not a stable atom. Nitrogen atoms are not stable because for atoms to be stable, they require or they need to have full energy levels, which is not the case here. So for nitrogen atoms to become stable, they require 3 additional electrons. So coming back to our covalent bonding, if we want the nitrogen atoms to be stable, and if it involves covalent bonding, you know, sharing of electrons, each nitrogen atom will then need to share 3 electrons. So you're going to have 3 electrons from one nitrogen atom, 3 from the other nitrogen atom. So a total of 6 electrons are going to be shared between the 2 nitrogen atoms. Now, when drawing or illustrating covalent bonding, what you're going to do is you're going to draw these circles, and the circles are going to overlap with one another. Now, of course, the circles are going to be representative of the atoms. The overlapping orbital, you know, hapo katikati, that is where we're going to place the shared electrons. At the center of each circle, you're going to place the symbol of the element. So in this case, it's N for nitrogen. So coming back to our electron configuration, nitrogen has 5 valence electrons. You know, these are the electrons that are found on the outermost energy level. Now, if nitrogen has 5 valence electrons and 3 of those are being shared, how many unbonded electrons are we left with? 2. So you're going to have 2 unbonded electrons as seen here. And of course, 3 are going to be in the overlapping orbital. We are done. It's as simple as that. Now, before we call it an end, I want us to count the number of electrons to ensure that they are actually 8, no more, no less. So let's start. We have 2 unbonded electrons. This is our lone pair of electrons. And we have 6 electrons that are being shared. So that makes a total of 8. So yes, the nitrogen atoms are now completely stable. One other thing I would like to remind you is this. When it comes to covalent bonding, we are not interested in the core electrons. You know, these are the electrons that are found in the innermost energy levels. We are not interested in them, and there's no need for you to illustrate them. The only electrons that are of interest are the valence electrons. And that is that. Now let's move on to the next one, which is fluorine. So fluorine also forms a diatomic molecule with covalent bonding. Now when it comes to fluorine, fluorine has the atomic number of 9. Therefore 9 protons and 9 electrons. So our electron configuration is going to be 2, 7. So each fluorine atom requires an additional electron in order for it to become stable. So it needs 1 more electron. So therefore each fluorine atom will need to share 1 valence electron with the other. So fluorine has a total of 7 electrons. So if you're sharing 1 electron, that leaves us with 6 unbonded electrons as illustrated. So the 1 shared electron is going to be in the overlapping orbital, and there we have it. Moving on to our second question, classification of types of salts includes normal and acid salts. Part A, give the name of another type of salt. Now, of course, this is also based on a Form 2 topic, salts. Now, in this topic, you are introduced to 4 types of salts. You have normal salts, acid salts, basic salts, and double salts. So if we look at part A, give the name of another type of salt, you could simply mention basic or double salt, and either of that is correct. Moving on to part B, Roman 1. Describe how an acid salt can be prepared using 0.1 molar sulfuric 6 acid and 0.1 molar sodium hydroxide. Now, I feel like before we can go straight to the answer, let us just remind ourselves what is an acid salt. Okay, actually, let's go through the 4 types of salts briefly. So the salts are, we have normal salts, acid salts, basic salts, and lastly, double salts. Now let's start with a normal salt. Now a normal salt is simply a salt that does not contain any replaceable hydrogen atom. This simply means that it does not have any hydrogen atom in its structure or in its chemical formula. So whenever you have a salt such as sodium chloride, potassium sulfate, sodium carbonate, that is simply a normal salt. Now when you take such a salt, dissolve it in water, you're going to end up having a neutral solution. Moving on to the next one, acid salts. Now these are salts that contain a replaceable hydrogen atom. Now whenever you see the formula of a salt or the name of it and it has hydrogen in it, that is an acid salt. So for example, if you have sodium hydrogen carbonate, potassium hydrogen sulfate, sodium dihydrogen phosphate, you see that hydrogen? Those are acid salts. Now as the name suggests, if you were to take such a salt, dissolve it in water, then yes, it's going to have acidic property due to the presence of the replaceable hydrogen. Moving on to our next one, the basic salts. Now basic salts contain hydroxyl ions. So of course, if you have a salt such as basic magnesium chloride, basic lead 2 carbonate, or basic copper 2 carbonate, as you can clearly see from the chemical formula, all of these have hydroxyl ions. So yes, basic. Our last one, double salts. These are salts that have 2 different anions or cations. So for example, hydrated potassium aluminium sulfate, hydrated ammonium ion 2 sulfate. Well, yes, you can clearly see they are quite a mouthful. And my favorite, trona. Now, coming back to our question, we now know what an acid salt is. It has to have a replaceable hydrogen atom. So that means in this case, when we react sulfuric 6 acid and sodium hydroxide, we shall get sodium hydrogen sulfate. Now let's go through the equation first. So we have sodium hydroxide reacting with sulfuric 6 acid, leading to the formation of our acid salt, sodium hydrogen sulfate, and of course water, because this is a neutralization reaction. Acid, base, salt, and water, remember? Now coming back to the procedure, so what are we supposed to do to get this salt? Number 1, you need to have equal portions or equal amounts of the base and the acid. So in this case, let us use 25 ml. So add 25 ml of 0.1 molar sodium hydroxide into 25 ml of 0.1 molar sulfuric 6 acid. Heat the solution formed. Which solution is being formed? The sodium hydrogen sulfate. So we are going to heat it to saturation, allow it to cool in order for crystals to be formed. And there we have it. Moving on to our next question. Complete table 1 by writing the formulae of all the products formed when the metal nitrates are heated strongly. So again, this is also from form 2, salts. It's actually in the latter part of the topic. Pale where it says action of heat on salts there. Now let's remind ourselves of the effect of heat on nitrates. Now, when it comes to nitrates, all nitrates decompose on heating. All, guys, all. But the way they decompose or the compounds that are formed differs from one to the other depending on how reactive the metal is. Now, when it comes to the nitrates of the 2 very reactive metals, potassium and sodium, you find that they decompose to form a nitrite and oxygen. So in this case, when potassium nitrate decomposes, it will form potassium nitrite and oxygen. Now, that is how potassium nitrite is written as. Do you remember from 1 when you are told about how compounds are named, and you are told that if you have a compound that ends with ATE and one that ends with ITE, it simply means that the one that ends with "et" has more oxygen atoms as compared to the one that ends with "ite." And this is also the case. So nitrate is written as NO3, nitrite is written as NO2. So in this case, when potassium nitrate is heated, it decomposes to form potassium nitrite and oxygen gas. Moving down the reactivity series, when we talk about nitrates of calcium, zinc, lead, and copper, you find that on heating, they also decompose, of course, but the products that are formed are going to be different. They form a metal oxide, nitrogen 4 oxide, and oxygen gas. So in this case, if we have lead 2 nitrate, what will happen is that on heating, it's going to decompose to form lead 2 oxide, nitrogen 4 oxide, and oxygen gas. And those are the formulas formulae of the product formed. Now, on the very lower end of the reactivity series, where we have silver and mercury, you find that the nitrates of these two metals on heating decompose to form nitrogen 4 oxide, oxygen, and the corresponding metal. So if you have silver nitrate, it's going to decompose to form silver metal, nitrogen 4 oxide, and lastly oxygen gas. And there we have it. Question number 4. Zinc metal is extracted from zinc blende ore through the following processes: concentration, roasting, and reduction. Part A. Explain how the ore is concentrated. Now, this is from a Form 4 topic known as metals. So in this topic, you're going to learn about extraction methods of certain metals such as sodium, aluminium, iron, zinc, lead, and copper. Then you're also going to discuss properties of such metals. Now, if you want to have a head start on revision of this topic, be sure to check out my videos on Cyclic, where I discuss in detail about their extraction. Now, coming back to the question, we are being told that zinc metal is extracted from an ore known as zinc blende. Zinc blende is simply zinc sulfide. Now, what happens is that when you have these ores, they usually tend to contain a lot of impurities. Now, remember, when you're extracting a metal, your aim is to get as much of that metal as possible. You're not concerned about any impurities that are there. So what you need to do is that you need to concentrate as much of the metal as possible and remove as many impurities as possible. So this is where concentration happens. So concentration simply refers to a process that removes impurities from the ore. Now, in the case of zinc, this is done through a process known as froth flotation. Now, when it comes to froth flotation, step number 1 is that the ore is first ground into a fine powder. Remember, you're going to have ores that are going to be in solid form, you know, majiwe like that. Now, you want to grind it into a very fine powder. The reason for this is so as to increase the surface area to ensure that as much of the ore comes into contact with the chemicals you're going to later on add. So the first step, you're grinding it into a fine powder. And then after that, what happens is that you're going to mix the powder with water containing special oils. Now, the most commonly used oil is pine oil. So this is added, and then a froth is created. A froth is, come up, you know, povu, it's generated. Now, this froth is going to contain a lot of the minerals, you know, the metal that you're after. The impurities that were present in the ore are going to sink to the bottom. And then last step is simply you're going to skim the froth, dry it, and you're done. At this point, you have concentrated the ore by removing as many impurities as possible. Part B. Write an equation for the reaction that takes place when the ore is roasted. Now remember, I told you that zinc blende is simply zinc sulfide. So if you were to react zinc sulfide with oxygen, and that is what roasting means, it simply means heating of a substance in the presence of oxygen and under very high temperatures. So if you were to react zinc sulfide with oxygen under high temperatures, it's going to form zinc oxide plus sulfur 4 oxide. And there we have our equation. Question 5. Figure 1 shows how the solubility of oxygen varies with changes in temperature. Part A. Explain using kinetic theory why the solubility varies as shown. Now, if you look at the graph, you'll find that an increase in temperature decreases the solubility of oxygen. So that is what we'll start with. Solubility of oxygen decreases as temperature increases. Now, the reason for this is as you increase the temperature, you are actually increasing the kinetic energy of the oxygen molecules. So the oxygen molecules are going to gain more energy, and by doing so, they can easily escape from the solution, therefore decreasing the solubility. Part B. With reference to figure 1, explain the pollution effect that may be caused by a large increase in the temperature of sea water. Now, when it comes to the sea, we are going to have some oxygen dissolved in it. You remember, oxygen is slightly soluble in water, so some amount of oxygen is going to be dissolved in the water. And this is very important to sustaining marine life. You know, marine animals and plants that require oxygen for respiration. So what happens if you increase the temperature of the seawater? As stated in part 1, an increase in temperature decreases the solubility of oxygen. So you're going to have less oxygen dissolved in the seawater than before. And this is going to be disastrous to the marine life, to the plants and animals that are present, because it means that less oxygen is going to be present in the seawater for them to utilize. By the way, if at any point you feel like I'm taking you too fast, just pause the video, rewind, assimilate the information that is here and then just continue. Now, moving on to question 6, a flow diagram for production of sulfuric 4 acid is shown in figure 2. So we have a flow chart there, starting with sulfur, and at the end of it, we have sulfuric 6 acid. Part A, state the optimum conditions necessary for carrying out the reaction in Unit 2. Now, if we look at Unit 2, we have production of sulfur 6 oxide. That means we are going to have a reaction between sulfur 4 oxide and oxygen, leading to the formation of sulfur 6 oxide. Now, since I had promised you that this is going to be a revision exercise, let us go through the flowchart, So this flowchart is based on the contact process, the large-scale manufacture of sulfuric 6 acid. Now, in Unit 2, we have the production of sulfur 6 oxide. So the optimum conditions that are required in this part, which is also known as the catalytic chamber, is number 1, temperatures of 450 degrees Celsius, pressures of between 2 to 3 atmospheres, and of course, the presence of a catalyst. Now, there are 2 types of catalysts that can be used, vanadium 5 oxide or platinum. Now, I want you to think and tell me, why would vanadium 5 oxide be the preferred catalyst? Actually, for 2 reasons. Reason number 1 starts with a C. Yes, because it's cheaper. And reason number 2 is that it's less poisoned. Now, I want to say this. Students sometimes write that vanadium 5 oxide is cheap. It's not cheap. It's cheaper compared to the cost of platinum. Now, when you hear about a catalyst being poisoned, this simply refers to the damage of a catalyst. So if you have a catalyst that can be damaged quite easily, that means you're going to need to replace it quite often, which will make the process or the production quite costly. So of course, vanadium 5 oxide is preferred. Now, one last thing I would like to mention with regards to temperature and pressure. Now, when it comes to temperature, you'll find that actually low temperatures are preferable in this situation. And the reason for this is because reaction of sulfur 4 oxide with oxygen leading to the formation of sulfur 6 oxide is exothermic. It leads to the production of heat energy. Exothermic reactions work best under low temperatures. Now, in case you're wondering, then why aren't we employing low temperatures in this case? It's because at low temperatures, the reaction is going to be very slow. So, a compromise is reached at around 450 degrees Celsius. Now, one other thing regarding the pressure. In this case, high pressures will actually be preferable. That means that if we have the reaction maintained at high pressures, it's going to lead to a high yield of sulfur 6 oxide. More sulfur 6 oxide is going to be produced, which will be actually very nice. But you will find that the pressures that are being employed are 2 to 3 atmospheres, not quite high. Now, the reason for this is because maintaining high pressures is very, very expensive. So again, a compromise is attained at around 2 to 3 atmospheres. Okay, enough with part A. Let us proceed to part B. Stage 2 takes place in 2 steps. Describe the steps. Now, stage 2, of course, this leads to the production of sulfuric 6 acid. So number 1 is that the sulfur 6 oxide that has been formed is going to be dissolved in concentrated sulfuric acid to form oleum. The oleum will then be diluted with water to form sulfuric 6 acid. And there we have it. And those are the equations representing the process. Okay, question 7. The following equilibrium exists in aqueous ammonia. Now guys, aqueous ammonia is simply ammonium hydroxide. So ammonium hydroxide partially dissociates in order to form ammonium ions and hydroxide ions. Now, due to the presence of hydroxide ions, this is going to be classified as a base. Remember, it's the hydroxide ions that actually determine the basic properties of a solution. Now, part A tells us, with reference to this equilibrium, explain why ammonia is a weak base. So we already know aqueous ammonia is a base, but the question is asking us, why would it be a weak base? Now, the reason for this is because aqueous ammonia partially dissociates. Now, there are 2 types of bases with regards to strength. We have strong bases and weak bases. Now, a strong base is one that completely dissociates in water, leading to the formation of a lot of hydroxide ions. Now, this is, for example, sodium hydroxide. Now, when it comes to weak bases partially dissociate. Some molecules dissociate, they break down, leading to the formation of hydroxide ions, while some don't. So, at the end of it, you're going to have fewer hydroxide ions, and therefore, this makes them a weak base. Part B, When aqueous ammonia is added dropwise to aqueous copper 2 sulfate, a blue precipitate is formed. The blue precipitate redissolves, giving a deep blue solution. Write the formula of the substance responsible for the blue precipitate and the deep blue color. Okay, so we are going to have a sequence of color changes here. Now, our starting point is copper 2 sulfate. This is, of course, is a solution. The reason why it's a solution is because copper 2 sulfate is a soluble salt. Now, this, of course, is a blue solution. Now, when you add a few drops of aqueous ammonia, what happens is that a blue precipitate is formed. So you're going to get a precipitate. A precipitate means an insoluble salt has been formed. Now, if you continue adding aqueous ammonia, the blue precipitate redissolves until it gives you a deep blue solution. Now, what is the reason why we are getting a blue precipitate? Now, if you have copper 2 sulfate and aqueous ammonia, remember aqueous ammonia is simply ammonium hydroxide. These two react with one another, leading to the formation of copper 2 hydroxide and ammonium sulfate. Now, copper 2 hydroxide, as with most metal hydroxides, is insoluble. And that is the reason why we have a blue precipitate formed. Now, in addition of excess aqueous ammonia, what happens is that a complex salt is formed. Now, this complex salt is soluble, and that is the reason why it dissolves, forming a deep blue solution. Whenever you hear the term solution, it means a soluble salt has been formed. Now, the complex salt that was formed is known as tetraamine copper 2 ion, and it's deep blue in color. Now, the chemical formula for this is that. Now, some students tend to find this a little bit challenging. Okay, I have to be honest. If I were a student too, I would find this challenging too. Now, what I tell my students is this. Just remember the name, and it's going to give you a hint, or it's going to help you recall what the formula is. So let's look at the name. We have tetraamine copper 2 ion. Now, tetraamine. Amine is simply a compound that is derived from ammonia. So in this case, it's the NH3. Now, we are being told tetraamine. So that means we have 4 of these. So NH3 enclosed, 4 at the bottom. Copper comes before the NH3, and then we are going to enclose all of these into brackets, and then finally place the +2 charge at the top of it, because the +2 charge is not just for copper but for the whole complex ion. And there we have it. How easy is it? Question 8. The molecular formula of 2 straight chain hydrocarbons is C4H6. Part A. Give the general formula of the homologous series to which the hydrocarbons belong to. Now, when you talk about hydrocarbons, these are compounds that contain carbon and hydrogen only. Now, there are 3 types. We have alkanes, alkenes, and alkynes. Now, each of these 3 has its own general formula. Now, the general formulas are as follows. So, for alkane, we have CnH2n plus 2, alkenes CnH2n, alkynes CnH2n minus 2. Now, in this case, for example, we have our hydrocarbon that has 4 carbon atoms. Now, if we look at the general formula of alkanes, if we have a hydrocarbon with 4 carbon atoms, we are going to end up having hydrogen atoms that are 8. So that means it doesn't belong to the alkane group family. Moving on to the second one, alkene. With the alkene, it will have a molecular formula of C4H8. So again, no. And the last one, CnH2n minus 2. So if it belonged to alkyne, it's going to have, okay, it's the correct one, C4H6. So in short, these hydrocarbons belong to the alkyne group. Now they have the general formula of CnH2n minus 2. Part B, draw the structures of the 2 compounds and give their names. And those are the structures. Our hydrocarbon has 4 carbon atoms, and it's also an alkyne. So what is its name going to be? It's going to be butane. Now, in this case, we are being asked to draw the structures of 2 isomers. Why do I say that these are isomers? It's because they have the same molecular formula, but they will end up having different structures. Now, for the first one, we are going to place our triple bond. And yes, triple bond, because all alkynes have at the very least a single triple bond. Now, we are going to place our triple bond on the first carbon atom as such. Now, once you're done, you're going to fill in the remaining carbon atoms. So remember, there's supposed to be only 4 carbon atoms. And for each carbon atom, there can only be 4 bonds, no more. So let us place in the hydrogen atom. So for the first one, tunaweka hydrogen hapo, and as you can see, it's already complete because it has a triple bond with the next carbon atom and a single covalent bond with the hydrogen atom. Now moving on to the second carbon atom from our left, this is already full. The third one has two open spaces, so we're going to place a single hydrogen atom at the top and another one at the bottom. Now for the last carbon atom, this has three open bonds. So for each of these, we are going to place a hydrogen atom. Now if we count the number of hydrogen atoms, it's supposed to be 6, which it is. Now for the next one, we are going to move the triple bond to the second carbon atom, and then of course fill in the hydrogen atoms as necessary, and we are done. Now the first one is going to be but1-ine. Now the reason for the 1 is because the triple bond is on the first carbon atom. The second one is going to be named as but2-ine because the triple bond is on the second carbon atom. Question 9. Water hardness may be temporary or permanent. Part A, write the formula of an ion that causes temporary hardness. Okay, let's just remind ourselves. So we have temporary hardness and permanent. Now temporary water hardness is caused by the presence of hydrogen carbonates, that is calcium hydrogen carbonate or magnesium hydrogen carbonate. This can be easily removed by boiling because the hydrogen carbonates decompose. Now when it comes to permanent hardness is caused by the presence of a different type of salts. Now it's caused by the presence of sulfates of magnesium and calcium. So for part A, our answer is going to be the hydrogen carbonate ion, and that is its formula. Part B, temporary hardness can be removed by boiling. Give one disadvantage of using this method in industries. Now just imagine if you have large-scale industries for removal of temporary hardness of water, these are going to consume a lot of energy, which will make the whole process expensive. So that is the disadvantage. Part C, state one method that can be used to remove permanent hardness. Now there are several methods, so I'm going to mention just a few. Addition of sodium carbonate solution, the ion exchange method, distillation method. Any of these is correct. Moving on to question 10. Part A, figure 3 shows an energy level diagram for the formation of hydrogen fluoride. Now this is a question based on a topic called energy changes in physical and chemical processes, which is a Form 4 topic. Now I know for most of you, you've not yet been taught this question, so I'll try my best to include relevant information that will make it easier for you to understand. So number 1, what is an energy level diagram? Now an energy level diagram is simply a way to illustrate the energies of products and reactants. Now we know that in a particular reaction, we'll always have the reactants and the products. Now energy level diagrams are used to show the energies of the products and reactants as seen from the above graph. Now in this case, we are being told to use the energy level diagram to obtain or to calculate the enthalpy of formation. Now enthalpy is simply a change in the heat content. Now it's usually denoted by the following symbol, delta H. Now if we want to calculate the enthalpy change during the following reaction, we can easily do so by the use of this formula. So enthalpy of products minus enthalpy of reactants will give us the enthalpy change of formation for hydrogen fluoride. Now going back to the graph, the enthalpy of products of course is 100. The enthalpy of reactants is 370. Now this gives us negative 270 kilojoules per mole. Now let's break down this value. Let's start with the negative sign. The reason why we have this negative sign is because this reaction is exothermic. Now, exothermic reactions are reactions that lead to the production of heat energy. Have you ever done any experiments in chemistry and you're in the lab, you're mixing certain chemicals, and you finally find that the test tube or boiling tube you're holding has become warm to the touch? Then that is an exothermic reaction. Now, endothermic reactions, on the other hand, they absorb heat energy from the surrounding. Now, in such a case, you'll find that if you carry out an endothermic reaction, you'll find that the apparatus you're holding might be cool to the touch. So exothermic reaction is what happens in this case. So we are having heat energy being evolved, and that is the reason why we are having the negative sign. Now, one thing with regards to exothermic reaction, because we are having heat energy being evolved, you find that overall the final amount of energy is always going to be less. So the enthalpy of products is always going to be less to that of reactants, because we are going to have energy being lost to the surrounding. Now part 2, activation energy for the reaction. So what is activation energy? Now activation energy can be defined as the minimum amount of energy required by a reacting molecule to be converted into a product. Okay, that is like kizungu mingi. Simple terms. Activation energy, it's simply the amount of energy that is required for the reaction to proceed in order for the reactants to be converted to products. Now, how are we going to obtain the activation energy for this reaction? Simple. We are going to take the 411, which is our value for the activation energy, subtract 370. That gives us our activation energy, which is 41 kilojoules per mole. Moving on to the next question. At high temperature, hydrogen and oxygen react as shown in the following equation. In an experiment, a mixture containing 200 cubic centimeters of oxygen and 300 cubic centimeters of hydrogen was heated to form water. Part A, determine which gas was in excess and by how much. Now, we are going to use the mole ratio to guide us in this. So if we look at our balanced chemical equation, we have 1 mole of oxygen reacting with 2 moles of hydrogen. So the mole ratio of oxygen to hydrogen is 1:2. Now let's go to the volumes. We have 300 cubic centimeters of hydrogen. So if 300 cubic centimeters is equal to 2 moles, that means that 1 mole will be equivalent to 150 cubic centimeters. So 150 cubic centimeters of oxygen will react with 300 cubic centimeters of hydrogen. So which gas was in excess? Oxygen. By how much? 50 cubic centimeters. Part B, calculate the volume of water that was formed. Now, how many moles of water were formed? 2. So that will be equivalent to that of hydrogen, which is 300 cubic centimeters. Part C, explain how one would confirm that the product was pure water. Now, you can use physical properties of water, for example, determining the boiling point, which is about 100 degrees Celsius at 1 atmospheric pressure, freezing melting point of 0 degrees Celsius at sea level, density 1 gram per cubic centimeters, and such. Question 12. Silk and rubber are examples of natural polymers. Part A, give the name of another natural polymer. Okay, what are polymers? Now, polymers are complex compounds that are formed from many repeating units. These repeating units are known as monomers. So if you have something that is repeated again and again and again until finally you have this complex long molecule, that is what is termed as polymer. Now, this is covered in Organic Chem 2, which is in Form 4. So part A, give the name of another natural polymer. We have several: wool, starch, cellulose, glycogen, and yes, you heard me right, starch and glycogen. By the way, if I may use an example of glycogen. Glycogen is a polymer because it's formed from many repeating units of glucose. So in this case, glucose is the monomer which forms glycogen. Same goes for cellulose and starch. Now part B, state the sources of silk. Silkworms. Part 2, natural rubber. This, of course, is from the rubber tree. Question 13, give the formula of the compound referred to as rust. Now, rust is hydrated iron 3 oxide, which is written as such. Now, the reason you have a full stop and then 2H2O is because, as stated before, rust is a hydrated salt. Now, moving on to part B. 4 test tubes were set up to investigate a rusting of iron as shown in figure 4. The setup was allowed to stand for 1 week. Explain why. Roman 1, no rusting took place in tube 3. Now, the reason why there was no rusting is because there's absence of oxygen. Remember, for rust to take place, there are 2 conditions that need to be present, and that is oxygen and moisture. Now, in test tube 3, when the water was boiled, all the oxygen dissolved in it was expelled. Now, by covering this with a layer of oil, it prevented any entry of air. Therefore, no oxygen, therefore no rusting. Roman 2, select the test tube in which there was highest amount of rust. Give a reason. Now, if you look at the test tubes, there will be rusting in test tube 1, 2, and 4. But out of these 3, more rusting will take place in test tube 4. And the reason for this is because of the presence of the salt solution. Remember, we have 2 conditions that accelerate rusting, that ensure that rusting occurs at a very quick rate. And that is salty conditions and acidic conditions. So due to the salt solution, we are going to have a faster rate of rusting in test tube 4. And that, ladies and gentlemen, brings us to the end of part 1. Be sure to check out part 2, where I'll be continuing with paper 1. See you there.